Hello, my dear students. Welcome to the online lecture video series on electromagnetic theory by AVS Stephen. In the last class, we have discussed about unit vectors in various three-dimensional coordinate systems. In the current module, we will discuss differential elements in this coordinate system. Before we discuss differential elements, it would be easier for us to understand the importance of them by looking at line integrals and surface integrals of vector. Let us dive into it. Line integral of a vector field. The general expression of a line integral looks like this. In this, curve C is the path along which we are taking the integration of the vector field V bar. dl bar is to represent that it is a line integral. Let us understand this. Let us understand this by an example. What is the physical significance of it and what can we intuit from it? Consider a non-linear path from A to B and assume that it is a motion of a body from A to B. Now, we intend to find out the work done by a force field in moving a body from A to B. Let us assume that the force field we would like to determine is this one. Now, you can see that its magnitude is different from one point to another point, thereby earning the name field. But for our easy, we have considered that the direction to be constant all over the place. Now, in this, the direction is always from left to right. It has never gone top to bottom or bottom to top at any instant. That means it is not possible for this force to induce a lateral displacement. It can only cause a longitudinal displacement. Now, I asked you to determine the work done by this force in moving a body from point A to point B. We know work done is equals to force dot displacement. But in our problem, the work done is not a vector, but instead it is a vector field. That means its value varying from one point to another point. Not only that, its displacement is also not a straight line. It is a non-linear path. Hence, the direct dot product between them is not easy, or I can also say not possible. Hence, I cannot apply F bar dot S bar to determine the work done by that force. So what shall I do? So to answer that, what I do is I will determine F bar dot S bar at each and every point and then add all of them to get the total work done. That would be possible and easy. Let me show you how. That is possible from our mathematical principles of linear approximation of a nonlinear curve. Mathematics says that a nonlinear curve can be approximated as a straight line, but that straight line would be different at all different points. That is, any curve at any point can be approximated as a straight line passing through it. But you know, there can be infinite straight lines passing through a point. So what straight line would that be approximated to? It would be approximated to that straight line which is having slope same as that of the curve at that point. For example, if I consider this point, at this point I can determine the slope. If I know the expression of this curve, I can determine the slope at this point by dy by dx. That is the slope, and this is the point from the principle of y equals to mx plus c, where m equals to dy by dx. I can get a straight line, and that straight line would be linear approximation of the nonlinear curve at this point. I can also say this is nothing but the tangent of this curve at this point. There is a standard name. Now at every point I will be determining this tangent, and once I determine this tangent, I would dot this with the force field, and I would get the work done by the force field at this point P. But I don't want the work done at one point. I want the work done at all points from A to B, whereby the limits A to B f bar dot dl bar. dl bar represent the tangent to the curve at that point. Let us look into its physical significance. What does this line integral say? The line integral gives us the component of the vector field along the tangents to the curve. The differential element we have used is dl bar. This is called as differential length element, also called as differential displacement element. For a differential length element to appear or to come into existence, there should be change in at least one variable, or the change can be combination of multiple variables. What is the expression of this differential length element in various coordinate system? We would go to that question in our later topics, but now let us look at the surface integral in the same way as we looked at the line integral. Surface integral of a vector. The general expression of a surface integral of a vector field will look like, in this, again, this S represents the surface along which we are determining the surface integral of V bar, and this ds bar is at every point that is the normal to the surface. Let us consider a homogeneous flow field. Flow is constant over a plane, and it is in one single direction. It is flow of some energy elements. Now, assume this to be the flow. My question or my aim is to collect these elements using a ring which you have like. Now, how do you collect a ring? Is if it flows through it, I will be able to collect it. That is the answer. Right? If it flows through it, I will be collecting it. Now, more the number of energy elements passing through it, higher is the collection. Let us look how we shall place the ring in the field to have maximum collection. Let us consider scenario 1. This ring is placed horizontally. Now, what is the normal to this plane? Normal to this surface is in this direction, and the flow is in this direction. Now, from a common sense, for example, if this is the water flowing and I place a glass like this on top of it, like in line with it, the water would be just flowing over it. It would not be flowing through it. The energy elements are not flowing through it. They are flowing over and above it. So how much would be collected? No flow through the disk. Now let us look in the orientation 2. Here, look at the normal direction. The normal is directed this way. And the flow is in this way. You can see the flow is improved. There is a possibility of flow through this ring now. Improved flow compared to the earlier case. Now let us look into the other orientation. See, the normal to this is in line with the flow. This entire area is covered with flow. This is the scenario where I can have the maximum flow. The maximum flow through this surface is possible when the normal lies in line with the field. When the normal is in line with the field at every point. Now, in the diagram, in the shape we have considered, the normal is having the same shape, but sometimes it is possible that the curve has different normals at different points. Right? In that case, at each point, the flow should be in line with the normal. Only then maximum collection or maximum flow through the surface is possible. Now, what can we intuit from this? We can see that the maximum flow is possible when the normal is aligned with the flow. Now, what is the physical significance of the surface integral of a vector field? The surface integral of a vector field, as we have seen, is of the form f bar dot ds bar, where ds bar is normal to the surface S at the given point, and what it is doing is it is accumulating all the components of f bar in the direction similar to that of the normal at any given point. It is generally used to determine outward or inward flow through a surface. Now that we have discussed it, I should also discuss the relation between a closed loop and a surface. In the last section which we have discussed, where a line integral has been discussed, I told you that if there is a change in one element, it is possible for us to have differential length. But For a differential surface element to occur, it is very clear that an area is a two-dimensional quantity. So there should be change in at least two variables. But not just that. If you begin on a point at the circumference of any loop or any path, you move along its direction, then finally you should be reaching at the same path, same point where you have started. If you are able to do that, then you can say that the path you have taken is a closed path. Now, if a path is closed, then obviously you can have a surface. Until and unless a path is closed, you will not be having a surface. So, the differential element we use is ds bar. This ds bar is nothing but the normal to the surface at the given point. Remember that dl bar we have used is tangent to the path you have taken at any given point. ds bar is the normal to the surface at any given point. Now, it is obvious that it should be changed. There should be change in at least two variables, but not just that. That the change in variable should be closed. That is, where you have started, if you move along the tangent of the path, you should again come back to the same point. Only then you would be having a surface. Now, let us look at the volume integral. Physically, it is not possible to decompose a vector into a three-dimensional component and accumulate it over a region. Hence, volume integral does not exist for vector, at least in three-dimensional case. A volume integral would be possible only for a scalar. And it would be looking like integral of S dV over a volume V, where dV is the differential volume element. Now, for this differential volume to exist, there should be change in all three variables. And not just that, the change should be closed, or shall I say that only closed surface can have volume inside them. Having said that, let us determine the expressions for various differential elements in three-dimensional coordinate system. Imagine that this is the three-dimensional Cartesian coordinate system we have, where this represents ax cap, this represents ay cap, and this represents az cap. Ay cap is going into the plane, going into the screen of your ax cap is from left to right, and az cap is from bottom to top. Now, if you are at a point A, assume that there is change only in x direction. Then you would be moving along ax cap by the amount of dx. This vector would be dx ax cap. I can get that from a bar equals to mod a cap. Now the direction is along ax cap, mod a is dx. So this vector is dx ax cap. If there is change only in y, if there is change only in y, I will be again moving in ay cap direction, but with the magnitude dy. If there is change only in z, then I would be moving in az cap direction with a magnitude dz. Now, this is the point I would be reaching if there is change only in x. This is the point I would be reaching if there is change only in y. This is the point I would be reaching if there is change only in z. But what if there is change in all x, y and z directions? Again, this is the same coordinate system which we have considered. Now let us use the principles of superposition, or I can also say parallelogram law, for vector addition. I am at point A and I assume that the change is only along ax cap, giving me dx ax cap. After that, I am here, and from this point, let me assume that there is change only in y. Now, I have reached somewhere over here. But that is not over, because there is also change along z. Now, if I assume that the change in that z direction would be from here, now I have reached to my point B here. Now, what is the vector joining A to B? The vector joining A to B is this. How did I get there? I got there as sum of dx ax cap plus dy ay cap plus dz z cap. This is the total differential length vector. Now, out of these three, for dl to exist, the minimum requirement is that the change to be in at least one variable. Nobody is stopping you from making change in 2 or 3 variables, but minimum requirement is that of a single variable. Now, imagine a cuboid form. This is the cuboid. See, this is our point B, where there was change in x, y and z. This is our point where there is change only in y. This is our point where there is change only in x. Imagine that this cuboid has been formed. You know that this is we are able to see only 3 faces of it, but you know that there are 6 faces, right? Let me draw you those faces which will not be generally visible from any perspective, right? But see, you can now see intuitively all the 6 faces, right? Those 6 faces are 6 different surfaces. See, the top face, this is the top face, front face, left face, bottom face, back face and right face. These are the 6 faces of a cuboid. Now, each face is a surface. Each surface has a normal. What are various normals? Let me rephrase the sentence. What are the normals of this surface at various points? Those normals, as you have seen, are nothing but are differential area elements. Consider a top face, just a top face. Let me see this. This is ax cap, This is AY cap. The changes are in AX cap and AY cap only. AZ cap is constant, and if I start from here and go along the tangent to this, you can see that I am going here, 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 and coming here. Right? See, I have formed a closed loop, thereby forming a surface. In this surface, the changes are only in x and y. The changes are dx ax cap and dy ay cap. Now, the area of the parallelogram formed by these two vectors can be obtained by the laws of physics, that the area between two vectors a bar and b bar can be obtained by a bar cross b bar. Now, if I use the principle here, I would be getting dx ax bar cross dy ab. Now, magnitudes can be separated, that is dx dy times that of ax cap cross ay cap. Ax cap cross ay cap is nothing but a az cap, that is our normal. Our normal to the top surface is dx dy az cap. That is the differential area element for the top surface. Whereas for the bottom surface, it would be minus dx dy az cap. For the right surface, it would be dy dz ax cap. For the left surface, it would be dy dz minus ax cap. For the front surface, it would be dx dz minus ay cap. And for the back surface, it would be dx dz ay cap. How we got there? You try it on your own. We would also discuss that while we discuss divergence of a vector. I have asked you to do that. You please do that before we go to the next module. Whereas the differential volume can be identified again from the laws of physics from vector algebra, that vectors a bar, b bar, c bar form a volume. Their volume can be identified as a bar dot b bar cross c bar. From the same principles, if I do that, I will be getting the value of dx dy and dz. This is the differential volume element in a Cartesian coordinate system. Now, let us look in cylindrical coordinate system. In cylindrical coordinate system, the variables are rho, phi, and x. And the change in variables are, as you know, independent, and they are d rho, d phi, and dh. Now, what would be the complete differential length element? What would be the differential area elements? And what would be the differential volume element in a cylindrical coordinate system is what we will be seeing now. Before we discuss that, let us look into an interesting topic. What is the path length because of an angular displacement? The line which you are seeing here is the reference axis and cylindrical coordinate system, and this is the reference point. Distance from this point would be rho, and the angle with this reference axis would be phi. Now consider 2 points, one point rho 1 comma phi comma 0, and the other point rho 2 comma phi comma 0, where rho 2 is greater than rho 1. They are on the same line, thereby giving the angle phi comma. See, the angle phi is the angle between the reference axis and the positional vector. They are same for both the points, but the distance from the reference point to the given point are different. Rho 1 in this case and rho 2 in this case. Now, assume that they have experienced similar angular displacement. They have experienced similar angular displacement. They have experienced angular displacement. That means the distances from the center have not changed. They have only moved along the counterclockwise direction. You know, the locus of the constant phi is nothing but a circle. Now we have not reached this full circle as such, but just an angular displacement, just an arc. Now what I want you to determine is what is the length of this arc and what is the length of this arc. What is the relationship between them? Where this is the angular displacement which you have experienced. It is very clear that the path travelled by the first point is much smaller in magnitude compared to the path travelled by the second point. That means path length is not just dependent on angular displacement, but is also dependent on the magnitude. The magnitude here being rho. For different values of rho, we are having different displacements, or let us say the magnitude of path length. Total path length would be rho d phi and along the direction of a phi cap. This is displacement vector because of change in phi. This is an interesting topic for you to understand. If we understand that, it would be easier for us to discuss differential length in both cylindrical and spherical coordinate systems. Let us look at differential length in a cylindrical coordinate system. Consider a body situated at a point rho comma phi comma h, and let us assume that similar to that of the Cartesian coordinate system, that there are changes in both rho, phi and h. Now let us determine what is the displacement vector, and thereby we can have total differential length. The path length due to rho is d rho. The path length due to h is same as that of path length due to rho, that is dh, whereas path length due to phi is not d phi, instead it is rho d phi, but it is along the direction of a phi cap, similar to that of rho and h. Now the differential length is the path length due to rho plus path length due to phi plus path length due to h. This is the differential length vector. Now once you have the differential length vectors, we can also determine 6 different differential surface vectors by combination of them. For you to do that, you should know the relationship between the unit vectors in cylindrical coordinate system. If by chance that you don't know, let me give you a rho cross a phi equals to ah. If you remember this equation, by rotating these variables, you can get the remaining 2 expressions. The next expression would be a phi cross ah equals to a rho cap. See this? This vector has gone here. This vector is gone here. Just a rotation. Now again, the next would be, this would be going here and this should be coming here. That is ah cap cross a rho equals to a phi cap. This is not just for cylindrical coordinate system. This applies for Cartesian coordinate system and cylindrical coordinate system and spherical coordinate system. You remember the first expression? The first expression in case of Cartesian coordinate system is ax cross ay equals to az. You rotate them, thereby you will be getting the remaining 3. And in spherical, it is ar cross a theta equals a phi. That would be giving you the other 2 expressions. Now, what is the differential area elements? Just by crossing 2 vectors at a time, it would be easier for you to determine the differential area elements. So, I'd be requesting you to do that. And differential volume is very straightforward. That is product of the path lengths because of all 3. That is d rho times rho d phi times dh. That can also be written as rho d phi dh. Excuse me, that it is written as theta. It can be written as d phi. Now that we have understood Cartesian coordinate system and cylindrical coordinate system, let us also look into the differential elements in spherical coordinate system. The variables in spherical coordinates are r, theta and phi. In this, r is distance measure just like x, y, z and rho and h, where theta is an angular measure. The angle positional vector is making with the z axis. Phi is here the same as that of a cylindrical coordinate system. It is the angle, the projection of positional vector is making with the reference axis. In general scenario, generally it would be an x-axis. The changes in r, theta and phi are also independent. They are dr, d theta and d phi. If you are at a point r comma theta comma phi, and if you have moved to a new point r plus dr comma d theta plus d theta comma phi plus d phi, what is the vector which is joining point A to point B? That would be a differential length vector. Here there are 2 angular displacements. It is very clear that the radius of theta is r, so the path length would be r d theta, whereas what is the radius of phi? It is rho. What is the relationship between rho and r? We have seen in the previous topics while we had discussed unit vector. I would request you to go back and visit them, where r equals rho equals to r sin theta is the result we'll be seeing in the previous classes. So the now differential length element would be path length because of r plus path length because of theta plus path length because of phi, where this is nothing but rho. Now you would be needing the relationship between these vectors to determine the differential area elements. ar cross a theta equals to a phi is the first expression. By right rotation, you can get a theta cross a phi equals to ar. Similarly, a phi cross ar equals to a theta. Using that, please determine the differential area elements. Now, what is the differential volume element? The differential volume element is again just the product of the path lengths, that is dr times r d theta times r sin theta d phi. That would be r square sin theta dr d theta d phi. This is the reference where you can see. Before I close my topic, let us refresh what we have seen. We have seen the differential length elements in Cartesian coordinate system. We have seen the differential length elements in cylindrical coordinate system. We have seen the differential length element in spherical coordinate system. Not just that, we have also seen the relationship between the differential length elements and differential surface element. We have also seen differential volume elements in all 3 coordinate systems. In the beginning, we have discussed the significance of line integrals and surface integrals of vector fields. We have also seen that volume integrals are not possible for vectors in three-dimensional coordinate system. It would be only possible for us to accumulate scalar quantities. Thank you. Please revise and try to answer the questions which are asked in this lecture. Let us meet in the next lecture.